Do we start or?
Yeah, it's starting now. Sorry.
Okay, no worries. Yeah, so that's about me from my PhD, from my current position and my PhD and also my undergrad. As you may or may not notice, I'm part of this doctor training program called Industrially Focused Mathematical Modeling, and I would like to talk about it a little bit more because it relates to how I become interested in network science and also assign networks in particular. Now, something different about our program is that our research project is tied with an industrial partner, and they will give us some problems they are interested in. And what we will do is to approach it mathematically. For me, my industrial partner is Tesco, the UK's largest supermarket chain. Like other retailers, it is characterized by a huge turnover, but relatively small margins. Then every single decision on the products might have a significant consequences on the overall sales or revenue. One primary problem here would be to understand the intrinsic relationships between products, including complements such as hot dog and hot dog bun. So they're sold separately but used together. They normally have more value when consumed together rather than alone, and also substitutes such as different types of berries. These product relationships are important in further decision making, such as to design the product catalog, to arrange the layout of products in both actual and online stores, to determine the stock level of different products, as well as the promotion strategies. Then in all these applications, the understanding of demand dynamics plays an important role here. So I'm also interested in the dynamics of networks as well. Talking about Tesco, I will also talk a little bit more about this real extraction problem we have done to extract these product relationships. So what we have is this sales transaction data. So each transaction or basket is given a unique ID. And we also know the store and the date this transaction happens, and also the products and their quantity in each transaction. In the original data of one generic store, we have over 1 million rows, 0.3 million transactions, and over 5,000 products. What we had done here to extract the product relationship is to interpret this relationship as how these product nodes are connected in this bipartite network. So this bipartite network is constructed by two types of nodes, one for transactions or baskets shown at these blue squares here, and the other for products shown at these red circles here. And these two are connected if the product appears in this transaction. So we can have this bipartite network, and then we have some assumptions on these product relationships. For example, complements are always bought together, substitutes are not bought together, but are bought with the same products. And then we have proposed some customized method here. For example, we use statistical test to determine the existence of the relationship and develop some similarity measures to quantify their degree, and finally apply community detection algorithms to detect or extract groups of complements and substitutes. We also validated with external data sets flavor compounds and recipes. For more details, please feel free to check our article online. And now if we have these product relationships, we can put them together and construct a network of products connected by both positive relationship, which is for complements, and also substitute relationship, which is negative. So now we actually have assigned networks with both positive edges and negative edges. And that's how I become interested in assigned networks. But it actually appears in many different contexts as well. For example, we can consider friend and enemy relationships in social systems, and excitatory and inhibitory functions in biological systems, and ferromagnetic and antiferromagnetic couplings in spin systems. Inside networks with both positive and negative edges have become an important model over recent years. just to make it clear, so for the remaining, we consider undirected sign networks. And an interesting future work is to extend it for the directed version. In the literature of sign networks, there is a relatively stable structure of structural balance. It is motivated by the following ideas in psychology, where a friend of a friend is a friend, an enemy of a friend is an enemy, and more importantly, it's like an enemy of an enemy is your friend. And mathematically, these can be interpreted as there is no cycle of an odd number of negative edges, which define these cycles to be negative. So there's no negative cycles. Harry has shown this structural theorem for balance, where a graph is structurally balanced if and only if we can find such bipartition of the graph with only positive edges inside and negative edges between the two, as shown here. And this makes us to consider the dual of this notion, where we can have negative edges inside, positive edges between the two. And this gives us this structural anti-balance notion. Formally speaking, this can be defined as there's no cycle with an odd number of positive edges. So we just exchange the role where positive and negative edges play. And Harry has also shown in his later papers that a graph is structurally anti-balanced if and only if we can find such bipartition of the graph with negative edges inside but positive edges between the two. And this actually provides the basis for the classification we would like to consider for sign graphs. To complete the story, we group all the remaining sign graphs to be strictly unbalanced, as shown here. So now we have 3 categories. And the idea here we have is to connect, to consider a very general case where the sign graph can have weights on the edges. So the weights can be different for different edges. And we would like to connect the signed weight matrix, which we show as W here, with the 1 corresponding to the graph where we ignore the sign. So that's the unsigned weight matrix W bar here, which can only be positive. And then we can connect sign networks with classic network signs and also the non-negative matrix, the results there. Then with these 2 matrices, we can start from these 2 special cases of balance and anti-balance through this unitary decomposition of W, which is U lambda U transpose, and also its unsigned one, which is W bar equal to U bar lambda bar U bar transpose. For the structural balanced case, what we can show is that the eigenvalue of the signed case is equal to the eigenvalue of the unsigned case, and the eigenvectors are correlated according to this I1 matrix. This I1 matrix actually shows the structure of this bipartition, where we can find 2 parts of positive edges inside, negative edges between the two, and the corresponding I1 matrix is to have the first part of value 1 and the other part of value -1. So these eigenvectors are related according to this I1 matrix. So they have different signs there. And for the structural anti-balanced case, what we can show is that the eigenvalues are the opposite, and the eigenvectors are also correlated according to I1 matrix, but now it corresponds to another bipartition with negative edges inside, the positive edges between the two. This is now hard to prove after realizing that W and W bar are similar to each other in the balanced case, and W and the opposite of W bar are similar with I1 in the anti-balanced case. So that's for these 2 special cases as shown here. And previously we have grouped all the remaining sign networks together to be strictly unbalanced, which is either neither balanced nor anti-balanced, which potentially have a lot of sign networks in this category. And we would also like to show some common patterns in this category as well. And what we can show here is that a sign network is strictly unbalanced if and only if the spectral radius, by which we mean the maximum absolute eigenvalue, will become smaller than the unsigned version. One direction is relatively easier to show from the previous result, because if the graph is balanced or anti-balanced, the spectral radius should be the same. And then for the other direction, we first show that if a graph is strictly unbalanced, we can find two walks between the same pair of nodes of the same length, but they are of different size, which means they are conflicts in the graph. And then these conflicts can further contract the spectral radius by the definition of matrix 2 norm. And we know that the ij term of w to the power of k sums over the walks between I and j. That could cause some conflicts there. And that's the structural properties I would like to discuss today. And then we would like to apply these structural properties to understand some dynamics on sign networks. And we can consider these signed random walks as a specific example here. By sign networks, what I mean here is these formulas still xt equal to p times xt minus 1, but now p is equal to the signed transition matrix. So W is a signed weight matrix, and D is still the diagonal matrix with degree of the nodes on its diagonal, which sum over the absolute values of the weights. So this dynamic is highly dependent on the properties of the signed transition matrix P here. So we can apply our results to understand this signed transition matrix so as to understand the signed random walks. For the special case of structural balance, we can show that the signed transition matrix has eigenvalue 1. And then if the graph is now bipartite, we can get the steady state of these random walks, which is x star here, and specifically as shown in this equation here. So in this case, the sign random walk can have, in the steady state, can have different sign in these two partitions, as shown before. So this partition has positive edges inside, negative edges between the two. And also, if we remove the first brackets, we retrieve the steady state of random walks in the classic case. So by adding signs to the graphs, the extra effect is from these first brackets. So now it depends on the initial state and how it spreads over these bipartition, encoding this I1 matrix here. As for the structural balanced case, and then for the structural anti-balanced case, what we can show is that the sign transition matrix has eigenvalue -1. Further, if the graph is now bipartite, we can get different limits for the odd and even time steps, denoted by x star O and x star E respectively, where the x star E is of the same format as before, but the I1 matrix corresponds to this anti-balanced partition. So it has negative edges inside, positive edges between the two, and the in odd time, this x star O is the opposite. So an extra effect from adding signs to the graph is that now it can have these alternating behavior of these dynamics. And for all the remaining case, what we call strictly unbalanced, we can show that the spectral radius, or the largest absolute eigenvalue of the sign transition matrix, becomes smaller than 1, and then the steady state is just 0. So nothing interesting happens here. So that's about the dynamical properties I would like to share here. So further, if you find something interesting, feel free to check our article online in this part. And what I would like to briefly mention here is that we have also shown that the previous results regarding structural balance and random walks can be extended for networks with complex weights as well. So first of all, why these complex weights could be interesting to us? It actually appears in many systems as well because we can consider the Hamiltonian of a quantum system. The off-diagonal term are complex values, and also in this image clustering sighting, with complex values, we can not only encode the similarity between the two figures, but also the optimal rotation angles to achieve this optimal similarity value between these two. So we can do finer clustering of the figures. And to show this correspondence between sign networks and complex weighted networks, we should also notice that if the phase of this complex value can only be 0 or pi, it actually reduces to the sign networks. So there's a nice correspondence between sign networks and complex weighted networks. I think I have some slides for some other topics if I have time to cover. I can briefly mention, or I can stop here.
Yeah, I think you still have time, and if you want to share some other topics, feel free to do so.
Yes, the other one of the things I would like to share is about community detection. So classically, we consider single membership community where each node can only belong to one community. But it's also possible that a node can belong to more than one community, and that relates to this mixed membership case, as shown on the right-hand side. And for example, we can consider certain protein belong to more than one community that is connected with them. And there is also a relatively new notion of discrete curvature on graphs, and then we can update the distance between the nodes in a sense that is similar to Ricci flow, and then we can disconnect them or making the communities like moving further and further to do community detection tasks. And I have some work here for mixed membership sighting, and then we have also proposed an integrated algorithm to detect communities both in the single membership case and mixed membership case. So that's community detection I would like to share here. And another thing is to use random walks to do mathematical modeling. Here I show an example of these slide mode dynamics. So we can put different sources at different position, and the slide mode will find optimal path to some extent between these food sources. And we can somehow model these dynamics with random walks with some extra reinforcement between the movement of the random walks and also the edge weights to achieve this goal. So that's a mathematical modeling part I would like to share. And as I mentioned before, at the very beginning, because I'm part of these initiative on networks and quantum information, so I'm also very interested in exploring the world of quantum from the angle of network science. And the first problem is how to construct a quantum network. There are different ways to do it, depends on how you consider a node and an edge. For example, we can consider the locality of qubits, and they share information as a node, and then they can entangle with other locality of qubits. So the edge is corresponding to the entanglements between these. And then we can build a quantum network there and consider the connectivity of these quantum networks. So that's something I'm also interested in. And finally, I would like to advertise a workshop we're organizing now together with Henry and Hanlin. That's between April 29th to May 24th this year in Stockholm, Sweden. And that's about dynamics and topology of complex network systems. And we welcome everyone to apply for our workshops. Yeah, that's it. Thanks for having me again.
Thank you. Thank you for your talk. And are there any questions from, okay, yeah. Oh, you are, okay. I thought you raised your hand. Any questions from the audience? So if I may, I have a question about this quantum network part. So you say basically you can construct a quantum network by considering the entanglement between this qubit, that right?
Yes.
And after you get such network, then what can you do on this network?
So for me, I'm more interested in the structural structure of these networks. So it's like different passes and how to combine these different passes to describe the entanglement between nodes that are not directly connected. That's related to this percolation that you are also interested in.
But
Yeah.
so the way of so that's about how to construct this network to achieve the goal, or the network structure is from experiments, or how this works.
I think it's pretty theoretical now. Yeah, you write the formula for each edge, and then from this formula, you write a formula for the path.
Okay, so
Yeah.
it's like an optimal network structure. You need to
Yeah,
find
optimal
that.
states. It's like perfect state, I think, from what they call it. It's a
Ah,
perfectly entangled state between these qubits.
okay. Lisa?
Hi, can you hear me?
Hey, yes,
Thank you for the talk. Very nice. I'm curious
thanks.
about one of the last work you showed, the one for with random walk for mathematical modeling. Can you formulate a bit
Yes.
more on and how do you apply that for cognition?
It's like a so it's like a reinforced random walks where this edge will be reinforced if random walkers going through this edge. So it's like for each food sources, we can put some random walks there, and then it will go through the path. But if they meet, and then these edges will be reinforced. So the shortest path can formulate through these reinforced process plus random walks, if it makes sense to you. It's like, so for these food sources, the random walk will keep spreading over the network. And then from these food sources, the random walkers will keep spreading the network. If these meet, and then these paths will be reinforced because the random walkers are more through this path. So they are optimal to some sense.
And how this model cognition?
Mhm.
How this model cognition?
And that's actually what we mean by this line mode. So
Okay.
they are like not very intelligent. So they don't have much information of the global scale. They only have information of their local neighborhood. Yeah.
Okay. Okay. Thank you.
No worries.
Any other questions? If no, I guess we can move forward to
Sorry.
sorry.
Hi.
Yeah, please.
Hi. Shak, nice to meet you.
Hi, nice to meet you. Yeah, I heard your name for several times. It's good to see you.
Thank you. So I had a curiosity more on the first work on the complementary and substitute products.
Yeah, I can
I
go to
liked
next slide.
thank you. I like
Yes.
the idea of using the sign networks to find these, let's say, complementary substitutes. I think it's an interesting approach. I was wondering if with the data, did you add like temporal information? So, for example, if you could see, let's say, the effect of a promotion, if or things of that nature.
Yeah, I think we definitely have these temporal data here because we have the date. We actually have the time, even second of this transaction happens. And what we have done here is to choose 3 months as a bucket to create this bipartite network and then get the relationship. So that's what we have done. And what we have mentioned in the future work is that we can do it for every bucket. And then we can see how these scores change over time. but we didn't really do it. Yeah.
Oh, okay, that's
I mean, the
interesting.
data allows us to do it.
Okay, that's interesting.
But we choose the 3 months where there's no like festivals like Eastern festival or Easter holiday. It's like this Christmas Day where there are a lot of promotions. It's like noise for us because we want to get this relationship where it's not muchly affected by
Normal,
these
yeah.
like external forces. So we somehow ignore these holidays and these big festivals. So if we do this temporal thing, we should definitely include their effects.
Okay, yeah,
And
so to
it's
say,
not
that's
very
interesting.
trivial to include it, yeah.
Okay. I was wondering, is the data actually publicly available, or is it
The Tesco data, no, but
Mhm.
I think there are similar data of baskets that are
Okay.
available online.
That would be interesting to see.
Yeah.
Okay. Also to compare as well. Okay.
Mhm.
Yeah. Sorry, just one curiosity if we have the time. Did you find something strange or particular when you looked at these complementary
Do
products
you mean
or
if I find some non-trivial complements and
yeah,
substitutes?
something that
Mhm.
they remind you?
Yeah, I think
Otherwise,
when we
I
do
will check
it,
the paper maybe as well.
I think
But
when
I
we
can
write the
check the
paper,
paper.
we
Sorry.
keep. Oh, I see. Yeah. When we were writing the paper, we keep emphasizing that we can find something that agree with our general understanding of complements and substitutes.
Yeah.
So
So
we put
nothing's
this in this. Yeah. Mm, yeah, I think it pretty much shows the shopping habits. So it's not very non-trivial.
nothing crazy. Okay.
It's
That's
towards the trivial part. Yeah.
Okay. Confirms our observation. I see. Thank you. Thank you very much.
Thanks. There's the chat. Oh, thanks.
Thank you.
Thanks.
Yeah, so Gab sent the paper in the chat.
Yeah, I see in the chat. Thanks for that.
And any other questions? No, I guess then we can move forward to the second part of the discussion.
I will do this to show my education here. Or should I stop sharing? That's easier. I can see everyone.
As you wish. If you don't have slides for this, you can stop sharing and.
Oh, do I need to prepare slides?
No, I mean,
don't realize that.
as you wish. If you have something to show, then of course you can. But if you don't, that's all right. It's quite casual. So as you wish.
Okay. Yeah, I will stop sharing because I don't really prepare slides for that.
Okay, so everyone, if you can unmute yourself or turn on your video. So
Yes, I can. Maybe I can start. I can start.
yeah.
Describe something that I would like to discuss today.
Yeah.
Yeah, I think I put something in my abstract about these, and that's pretty much relates to my postdoctoral experience. Because before I moved here, I'm really into this idea of doing either approaching the quantum part from network side or approaching the network part from the quantum side. So I'm very excited. I'm very excited of moving to Sweden as well to explore this new area. But when I arrived, I feel like people are really independent and into their own stuff. And so it's not very easy for me to really talk about quantum stuff from network side. So they are still doing these their own research, follow their own research path to doing either quantum stuff or other physics stuff, actually. So I really have no idea what I should do in the first place. And so that's why I feel it's very far from what I expected before I moved. And then, so something I mentioned is like managing your expectation. And the key part, I think, is to accept it. It's like accept what it is and then think of what to do next. That's the only thing we can do, right? Like our everyday life. Another thing I have tried and somehow works is that it's just to talk to as many people as I can. So I just approach everyone who has little research interest in networks. And there are some people, for example, in engineering, they can be interested in networks as well, but they are doing very different things, like they are approaching from the control side. And I can discuss with them, even though it's hard to like collaborate with them as well, but I feel like it's good to talk, just to talk. It's good to know what they are doing. Just open your mind to other things and know the groups there at least. The other thing is that I try to search for some senior people as well and try to find some professors with interest in network science and then send emails to them. That's how I found Kali at KTH and also someone at Karolinska as well. Just send them an email, a code blocking them. And the worst case is that they won't reply to me. So we have nothing to lose. And actually, Kali replied me instantly. It's like very fast reply. So that's really cheered me up at that point. So I find it really good. I just attend his group meeting every Monday, actually. So that's a good thing. Yeah. And also because I also talked to my PhD advisor at that point, and he has introduced me to some of his friends. And that's how I exchanged my first email with David Hunter at Uppsala University. And we have discussed some ideas. That's how we started this live mode project with random walks and some, because he's more interested in this biological collective behavior. That's how we created this project together. And then after this, he helped me to get the visiting scholar position at Uppsala, so I can regularly visit Uppsala from there and discuss our project. So something works, something not, and the only thing we can do is to keep trying. Give us some faith, believe ourselves. Yeah.
So at the very beginning, you said you intended to enter this quantum physics side, and you indeed had this review article on quantum network. So how does this collaboration started?
Oh yes, actually that's very because actually I met this one at Oxford when I finishing my PhD. We had some discussion about something else, but at that point I was very busy and I don't really have time. I just sent him an email. Okay, we can discuss it later. And I'm going to this job that is quantum networks. And actually, he's very interested in quantum networks. And then we keep discussing these ideas from there. And also, when I first moved to Nordita, I have invited him to give a talk. And also, I have invited him to visit us for a month, for a week. And he has also talked to everyone in our group at that point. That's where the collaboration really starts. Yeah.
Sounds good.
So that's also relates to the keep talking part. You just talk, you never know what happens.
Does anyone want to share something? Because I think this type of issue is more severe to this independent postdoc fellows. Otherwise, if you have a real supervisor, then you are assigned to some project. So you may.
Yeah, that's the other extreme. Yeah. It's that you are assigned to too many projects and then you don't have time to really explore what you are really interested in.
So I think unfortunately it's usually either this extreme case or the other extreme case. So
Yeah.
anyone want to share some of your experience or some of your idea about like developing new collaborations or I mean any suggestions?
Hi.
Hello.
No, I just wanted to say that I found interesting what you said, in a sense that I just started here in the UK as a postdoc, which I started to realize that it's different as a PhD. I was expecting more of like I am of course in contact with my supervisor and everything, but it's different when you need to start thinking about your own research projects, the research lines out of again, let's say, no, out of your traditional or what you did previously in the PhD. So I like your suggestions to just break, let's say, do not be afraid to just talk. I think that's something I will make a point of doing in the next days. But aside from that, I unfortunately don't have much to add except I will let you know. Well,
Thanks.
Actually, this reminds me of one question I have. I'm wondering, like this new projects you're starting, how different or how close are they to your previous ones, or to your, you know, how experienced are you on this new project? Because
Which new project?
like
Yeah.
after you start your postdoc, your new collaborators, new collaborations. Because for me, I think so when I consider the new collaboration, I think I mostly focus on something I'm more familiar with. Like when I talk to people, I talk about percolation and talk about critical phenomena stuff. And
Yeah.
because I feel like it's easier for me to start with. But I also feel this is not the always the best option, because you need to explore your own research area, or you can't only focus on percolation forever. So yeah, that's what I'm wondering, how
How
different.
similar it is from
Yeah,
my
yeah,
PhD.
my past project. Yeah, your PhD project.
I see. The thing is that my PhD project is highly dependent on Pascal, because I'm always start from real problems and then see which academic problems are related to it, and then see what we can contribute to these academic problems so as to provide a solution to these real problems as well, because I need to finish my PhD on the one hand and give a good answer to Pascal on the other hand. Somehow needs to combine these two, and it's until the very end of my PhD that I can really do something I'm interested in, then solely from the academic side, which is sign networks, and then I continue doing sign networks after in my postdoc as well. So from the sign networks part, I think it's like still highly related. But for the other projects that are more real world inspired, it's not so much related anymore, but it still can be considered as an example, because I'm also talk about complements and substitutes to start my talk, because I think that's a good example. And also how to balance these. I remember someone told me that because in academia it's solely very competitive, and we need to keep publishing, and that's easier to do with something we are familiar with. And then we also like to explore something new, and then that also takes time. So it's like a trade-off that we need to make a decision on. And for me, I would like to explore something that's interesting to me, and I think that's very important for me. Yeah. Mhm.
That's pretty nice. Yeah,
It's hard, I know.
but for me now, I'm the project I'm working with another senior professor. Like the techniques and the stuff is not what I really familiar with. I mean, although the question itself is quite interesting. So now I have stuck there for months.
I see.
So that's quite
Yeah.
frustrating though.
I think I know some people do, like they use similar like techniques they are familiar with, but they applied it for different problems. So they have different applications. I think that's the opposite of your case, right? That could also be like explore something new.
Yeah, it could be. Because I think I've never entered this real application area. So yeah, that could be also a more smooth path to start with, I guess.
Yeah, just
But analyzing the data could take a lot of time as well.
yeah. But yeah, it's true though. You can just use something you, let's say, know already, like a tool or a model or a methodology, just apply it on a different data set. You start to understand the issues in that field or application, and then you move from there. Something that makes it easy to explore something new without changing completely or having to learn all from zero. So that's a path, I guess, at least. This if we talk about, let's say, the trade-off you were talking about earlier, it's a way to cater to both our needs to explore new things or publish.
Yeah.
So this trade-off, I think it might be a very general issue because we also this problem also someone also brought up this problem yesterday in our meeting with our new director. So because we are in this wink, by the way, I'm also part of it. This so it's a combination of quantum mechanics, quantum information, and the complex dynamic network. So I think they are not traditionally very closely related areas. So currently, what happened is, like you said, everyone works on their own project, their own direction. I understand that's the idea of having such initiative is trying to somehow put them together, but in the end, it's just like the trade-off you said. People need to like publish more. So, but if you're entering a totally different field, it will take a lot of time for establishing new collaborations and everything, and there might be no good outcome in the end. So it's a risk to start this new thing. So I think for us at Nordita, this still remains a problem because I mean this is a postdoc position and only 2 or 3 years to the contract, so there's no infinite time for you to explore. Yeah, but I think we are trying to get some possible solutions without sacrifice too much or taking too many risks on this new collaborations. Yeah.
Because they don't really have a good platform or organization for us to really like combine these two fields. And as a postdoc, what we can do as a postdoc it's really hard to do it, right? To build a proper collaboration platform or a proper organization. That relates to the responsibility of a postdoc, I think.
Well, for responsibility, I think for independent postdoc, I find it might be slightly ambiguous in the sense that if you're assigned to, if you're funded by a specific project, then your responsibility is very clear on this project. But if not, then of course you have this freedom to do whatever you want, but still you have certain but somehow unclear responsibility in your everyday life.
Yeah, I think somehow in academia, the responsibility is in general not very clear.
Yeah. So I think I can make the advertisement again about our program. So let me put, because me and you are organizing this program at Nordita, and there's 1 week focused more on the dynamic and network side. And I think there might be some travel support or something still available. So if you are
I think
interested,
so, yeah, we'll have more.
you're
Yeah.
very encouraged to apply.
Feel free to apply. Stockholm in May is a good time to visit.
So let me put the program details in the chat just in case you're interested. Sorry, well, I don't know why my page is frozen. So the program is basically from several directions. One is dynamic on networks, so that's including propagation, epidemic spreading, or this diffusion process. And another direction is about a topological data analysis. And the third one is more about the inferences and optimization on networks. So if you find such topic might interest you, you're welcome to come. And later we'll also put the link on Twitter or somewhere, so you can check. And yeah, that's just a little random advertisement.
I think I find the link. I can send it.
Okay, thank you.
It's our program. Yeah.
All right. Anyone want to say something? So if no, I think it's roughly the time to come to an end. Thank you again for this great talk, and thank you everyone again for coming. And
Thanks so much.
yeah, see you in 2 weeks. Bye.
Thank you. Bye.
Bye.